everyone, I'm Peyton. As Bill said, I'm representing the math department. Today I'm going to try to do something that not very many people can do, and that's make math interesting. So, what I'm going to talk to you today are specific called orchard problems. Now, there's a subset of mathematics that they don't really have to do with orchards and trees, but it's a little bit easier to conceptualize as these problems representing those to kind of understand them. So the first one I want to talk to is, imagine you're at the corner of an orchard. So we know orchards when we're driving down those roads, farm roads, like there's just lines of trees, right? Imagine all these points as like apple trees. So you're standing at the corner right here. And so, I got that picture. I know, I tried to explain this to James Watson. He had a tough time understanding. But, the first, where is it? Where is it? Here? Oh, okay. The first, yeah, I made sure it wasn't here. Thank goodness. Thank goodness it's not here. So, question one. The first question I want to ask you is that if you're here and you're looking with your line of sight, is there any way that you won't hit a tree? Now, this is an infinite forest. So it goes on to infinity. It goes on forever. So at each of these points, don't think of them as regular trees, think of them as points on a line. So you got points at 1, 1, 1, 2, like, essentially. And so, to first kind of understand this problem, you have to think of, well, which trees can we see and why do we see them? And that just boils down to simpler terms. Your line of sight is exactly that. It's just a line on a plane. And so each of these lines represent wherever you're looking. So, as we know from, if we remember Algebra 1, horrible course for a lot of people, but lines have slopes. And the number that corresponds to that slope is going to tell you what tree you're going to hit. Like if you have a slope of 1/2, that means 1 over 2. Rise over run, not 1. And so you go up 1 over 2, rise over run. So essentially, this question just boils down to that which numbers will give you trees. And as we know, there's an infinite number of numbers, and all fractions too. So you can ask, well, if all these rational numbers that can be represented by ratios, can we see trees, which ones can't we see trees? It's a little bit interesting, not that interesting yet. But the answer to this is that the irrational numbers, which, as we know, we all know pi, right? The number pi, 3.141592655. It goes on forever, never repeats. And so that's what an irrational is. It can't be represented by a ratio, hence the name. So it can't be represented as a whole number over a whole number. So, big look. Now we know that rationals give us trees, irrationals give us gaps. That's kind of cool, but not really. So, give us the second question. It might get a little cool now, but bear with me. So now, if we picked a line at random, so say your eyes closed and then open them right there, what are the chances you're going to see a tree? That's a little bit interesting, but again, let's go back to what we know. We know that lines of sight are lines and lines have slopes, and slopes are represented by numbers. So all this is asking is, how many numbers are there? It's a silly question, but how many numbers are there of rationals compared to irrationals? Because if there's more rationals, then logic would tell you that you're more likely, when you pick a random line, that you're going to hit a tree. Since there's more rationals, you're more likely to pick a rational, right? Now we get into something that's a little bit more scary, for lack of a better term. But it's sizes of infinity. And so the rationals are what we call countably infinite. Bear with me here, I know. There's proofs for all this, I promise. But countably infinite, it doesn't mean we can really sit down and count them, because we'd be here for a lot longer than the 5 minutes I got. But what that means is that you can list them in a way that says, take this sequence on to forever, and you kind of capture them all. So you've captured every number in this sequence. All the rationals are countable, or listable, essentially. Now, irrationals, on the other hand, are what we call uncountable, which means there is no sequence that you can get where you can say, carry this on forever, and you're going to get every irrational number. They populate numbers so densely that they are infinitely bigger than rational numbers. So now if you're following, it kind of gets a little interesting, because if there's infinitely more irrationals than rationals, what does that mean? That means that of this set of numbers, your irrationals are going to account for infinitely many more than your rationals. So they account for 100%. So back to our original question, right? If you're picking a line at random, not only are you more likely to pick a gap, but it's 100% certain that you will pick a gap. You are in an infinite forest of point-like trees, and if you pick a line at random, there is a 100% probability that you will pick a gap in this infinite forest. Again, this only works for mathematically thin trees, which are trees with no width of their points, but yeah, I know. Kind of lowered it. But no, but there are trees. Like, I can pick a slope of 5, see a tree. There's infinitely many, right? That's a little, somewhat interesting. But I'm out of time, way out of time. So these problems get a lot more interesting once you do start talking about width. I promise they're not all these dumb, non-applicable to real life things. They get a lot cooler once you start giving trees width, and then you start asking a bunch of different other fascinating questions. But unfortunately, that's all I have to talk today. So thank you very much.